In this video, I'll discuss about decision tree. So decision tree is one of the most widely used machine learning language algorithm for classification, and it also gives very good performance. Let's look at some of the examples. So a decision tree is a natural and simple way of inducing following kind of rules. As if suppose if we know a person's age, a person's income and his family size along with his credit card spending details, then we can make the decision on his loan application. The decision tree classify instances as we already know by sorting them down the tree from the root to see some leaf node, which is further classification, or branches which provides a classification of the instance. So why we use decision tree? As we already know, decision tree, we use it for classification or to make predictions. So for classification, under different situations when we have just one variable and two categories, we can use it for standard classification tree. We can use standard classification tree. For responses where variable has multiple categories, then we can use C4.5 implementation algorithm. It can also be used to predict. So response variable is continuous. If the response variable is continuous, it can be used for linear relationship between predictors and response. And if it can also be used for non-linear relationships between predictors and response. Further, it can be used. We can use C4.5 implementation, and also we can use standard regression for linear relationship between predictors and response. So let's first understand the basic terms for the decision tree. So the basic root node is the point where we start the decision tree. It's a main attribute that we use, and it can be further splitted into multiple branches or multiple options, which we call it as decision node. And the further division with decision node we can do, and it could be that node could be called a terminal node or a decision node based on whether the node has a further classification or further branches. So here if we see that in the terminal node there is no further branches, so we call it a terminal node because it terminates there. In decision node, as you see, or a leaf node, you can see that it has further classifications, and this whole part of the decision tree, it is called subtree because it's again a tree within a decision tree. So let's have a look at one of the examples and learn like what decision tree is and how we can construct a decision tree. So suppose we have a person called John who wants to play tennis and tomorrow, and we wanted to decide whether he can play it or not. Now we have a training table where we have his details of past 15 days, and the details is regarding the weather and the weather details and his whether he played in last 15 days or not. So based on this data, let's decide that whether he could play on the 15th day or not. Let's go ahead. And so what we can do is in decision tree we can use a technique called divide and conquer, where we divide a detail into further subsets. We keep on splitting it into subsets until we feel that we have reached to the point where we can clearly say that he would play tennis or not. So for the decision tree, we would follow a basic algorithm, which is a greedy algorithm as we call it. So we will use a top-down recursive divide and conquer manner, whereby on the top we would have a root node, which we would split into further nodes, which we also term as leaf nodes. And the data which we are having right now, it's called training data, and input data can also be partitioned recursively, by which we mean that the same process is repeated at every stages, and we can use the information gain at the end to decide whether we have got the details or the information which assures us to stop, or we have to further split it into. Now where to stop for the while we are creating the decision tree. For that we can use the simple steps. Until all the samples for a given node belongs to the same class, we shouldn't stop. Or in the case where the remaining attributes, there are no remaining attributes for further partitioning, and for all the everything is towards one side, or it's inclined to one side, and there is no yes, there is only yes, or there is only no. In this case we should stop, or there are no samples left for further partitioning. So here we have the outlook. We have three different outlooks, and when it was sunny, John played for 3 days, as we see it in the red color. As we see in the red color, that he didn't play for 3 days, but he played for 2 days. When the weather was cloudy, he played for all 4 days. And in the when it was raining, he only played for 3 days. He didn't play for 2 days. And if we see the overall outlook, we can see that he played for 9 days and he didn't play for 5 days. And we clearly can't decide whether to go with yes or no, because it's really not completely over one side. So in this slide we can see that there are 3 days in which humidity was high, and on another 2 days the humidity was normal. So we can further classify this table based on humidity and create another table. And here we notice that when the humidity was high for 3 days, then John didn't play, but when the humidity was normal for 2 days, so there he played. So further, when the outlook is rainy, we can also divide it further based on wind conditions, as you can see it here. So we can divide the rainy conditions based on wind in weak and strong options. So for 3 days, when the wind condition was weak, we can see that John played during that time, but when for 2 days the winds were strong, so he didn't play during that time. So here we can see that when the outlook is sunny and the humidity is normal, when the outlook for cloudy is yes, when the outlook is rainy and winds are weak, then John plays. So from the data that we got for day 15, when the outlook was rainy and the humidity was high and wind was weak enough, there are most chances that he would play on day 15. So here we can see that there are 9 positives and 5 negatives, and again in the cloudy outlook we can see that there is 4 positives and 0 negatives, and in sunny it's 2 positives and 3 positives. So based on the number of examples of positive, how many positives we have or how many negatives we have, we can have confidence in our decision, and we can decide whether we should go with one we should go with one option or the other option. So on what basis we would be selecting, on which attributes we would be splitting them further. So if we split an outlook, we have 3 outlooks right here, and one of the outlook is in purest form, where we can clearly say that it's 4 positive and 0 no, and we can take a decision. But what with 2 others? In sunny, where it's 2 positive 3 negative, and in rainy, where it's 3 positive 2 negative. So these 2 are not in its purest form. So what to do with them? So here we can see that we have 6 positives and 2 negatives, which could be equivalent to 4 positives and 0 negatives. We cannot clearly decide on it. We want to use a measure that is symmetric on both the sides, that is positive and negative side. So at this stage of decision tree construction, it's really very hard to go ahead. So these 2 concepts called entropy and information can help us to move further in constructing decision tree. So entropy is the technique which will tell us how pure or impure one subset is. Entropy and information gain are both used for building decision trees, and it is being used widely in ID3 algorithm. So we would use this equation to calculate entropy once for one attribute, that is in our case it would be playing golf, and then later for both the attributes that would be playing the games and the outlooks, the three outlooks that we are having. Now let's move to information gain. Now information gain is all about finding decrease in entropy value after the data set is split on one attribute. The purpose of decision tree is about finding the attributes that returns the highest information gain, that is the most homogeneous branches. So the first steps, the once we calculate the entropy value as shown in this last slides, we will use this equation to calculate the entropy values first for one attribute and then for other attributes, and we will find out the most relevant information gain. So the entropy of each branches or the outlook for our case is added proportionally to get the total entropy for the split using this formula. So here if we see, this is the entropy value for the first just one attribute, and the second one is the attribute value for the split, the branch split, and the value that here we are getting is the value of information gain, that is the information gain that we are getting. Now this attribute with the largest information gain would be our decision node, and the branch which is having the entropy value of 0 would be in our leaf node. So a branch with entropy more than 0 needs further splitting, and the algorithm is run recursively until we don't have non-leaf branches or until all the data is classified. Thank you.